Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today I want to continue with the series that we've just started on writing a ray tracer from scratch in C++ using the SDL2 library. If you've seen the previous episode, we covered the basics of how ray tracing works, and I spent some time going over how we were going to set up the code and the general code structure for the project, and we ended by creating a color gradient image in a window. Now in this video today we're not going to create any new images, still going to only create the same one, but what I really want to do is to take the time to talk about camera geometry and exactly how we do all of the vector math calculations that we need to do in order to be able to create our virtual camera in our world space. So that's the topic of today's video. As I mentioned in the previous video, although I've titled this series Writing a Ray Tracer from Scratch, I am going to be using some code that I've written from a previous project, which was the linear algebra library series, also available on this channel. And I want to use the code from that for doing vector math and also matrix arithmetic as well. We're not going to need the matrix stuff today, but we will need to use the vector arithmetic side of that code. So we're going to take a quick look at that as well, but I'm not going to go over writing the code specifically to implement the vector class. If you're interested in that, you can look back at the previous video. I'll put a link in the description below. Anyway, I don't want to do a long introduction, so just before we jump in and have a look at exactly how we do all the calculations for the camera geometry, it just leaves me to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Okay, well, without much further ado, let's jump to it and let's have a look at the situation specifically regarding the geometry of the camera for ray tracing. So in the last video, we looked at the basics of how ray tracing actually works, and we ended up with this situation where we have rays cast from the pinhole of the camera through a screen and out into the scene. Where those rays touch an object, we stop and then cast a new ray towards the light source. From that, we can calculate how much light is striking the object at that point, and then we can compute the color of the pixel that corresponds to where the ray passed through the screen. In this episode, we're going to focus on the actual geometry of the camera. So to do that, let's first take our illustration from the last video and let's add a coordinate system so that we can see more clearly what is going on. So here we have a three-dimensional coordinate system with axes for x, y and z. Now we're going to cast our rays out through a virtual screen that will look something like this. The pinhole of the camera is, in this example, located at the origin of the coordinate system. The camera itself is pointing towards some point called the look-at position, so we can define the principal axes of the camera as shown here by the silver arrow. In this case, the look-at position is some point in the positive y direction, so the principal axis of our camera will lie along the y-axis, as you can see. Let's zoom out a bit so we can see more of what is going on. Now, the virtual screen here represents the image that we want to generate. So we divide it up into pixels as represented here by the yellow squares. In this case I've used a 9x9 grid, but in reality we would have as many pixels as we needed for the final image, be it 1280 by 720 or 1920 by 1080 or whatever. Then we simply cast a ray out from the pinhole of the camera through each pixel in turn into the scene, as shown here. This gives us an actual geometry that looks something like this, if we were to plot all of the rays at once. If we move around this a bit, you can see how the rays diverge from the start point at the pinhole. This is a really important point, and I've seen a number of people get this bit of ray tracing wrong. It is important that the rays that we cast into the scene form this kind of divergent pattern, rather than all being parallel. Otherwise it will not be a realistic simulation of the actual camera geometry. Okay, so let's take the rays away for now and focus on what we actually know about the geometry and what we need to calculate. So the screen itself has its own local coordinate system that we represent here by the two vectors u and v. These represent the locations of the pixels and form a coordinate system that is separate from the xyz coordinate system of the world that our camera is in. The problem that we need to solve is that given a pixel location in the two-dimensional UV coordinate system, how do we calculate the equivalent location on the screen in the three-dimensional XYZ coordinate system? We need to know that in order to cast the ray out from the pinhole of the camera through the screen. To calculate the u and v vectors in the three-dimensional xyz coordinate system, we need one additional piece of information, which is a vector that defines which direction is up. This is usually called the up vector of the camera. We also know the location of the camera, which I have here called CORG for camera origin, and of course we know the location of the point that we have set the camera to look at. This is usually called the look at position of the camera. Let's do away with everything that we don't need anymore, so that we can see the geometric situation more clearly. And let's change our angle slightly so that we can see more clearly what is happening. What we are going to look at now is exactly how we can use all the information that we have about the camera to compute the u and v vectors in the three-dimensional xyz coordinate system. Let's focus on just the u vector initially. The important thing to notice is that the up vector that we have defined and the principal axes of the camera given by the look-at position and camera origin form a plane, as shown here. The u vector is simply the normal to this plane. In other words, it is the vector that is perpendicular to both the up vector and the look-at vector. We can compute the vector that is perpendicular to two other vectors quite easily using the vector cross product. So we simply compute the vector cross product of the up vector and the look-at vector, and that will give us a unit vector in the u direction. Okay, so what about the v vector? Well, now that we have the u vector, we can notice that the u vector and the look-at vector form a plane, as shown here in green. The v vector is simply the normal to this plane, or in other words, the vector that is perpendicular to both the u vector and the look-at vector. We can then, therefore, calculate the v vector using the vector cross product of the u vector and the look-at vector. And that's it, really. Once we have the u and v vectors, we can use them to transform any coordinate in the two-dimensional uv coordinate system into a point in the three-dimensional xyz coordinate system. We will see how to do that in more detail when we come to look at the actual C++ code for doing this a little later in this video. But for now, that should be a sufficient overview of the geometry of the camera for ray tracing. Okay, so there we go. I said right at the beginning that I wasn't really going to talk about the vector math, and I'm not going to go into exactly what the vector cross product is in this video. It's well described, I believe, in my previous video from the linear algebra series, so you can of course go and look that up if you're interested. The code for computing vector cross products is also described in that video. One thing that I do want to say that's important about vector cross products is to understand how the orientation works, and we can understand that using something called the right hand rule. So to do that, we simply take our right hand, and what we're going to do is point this finger in the direction of one of our vectors. So let's suppose we were trying to calculate the u vector. So we point this finger in the direction of, for example, the up vector, and then we would point this finger in the direction of the principal axis of the camera, which is going to give us something like that. And then our thumb, as you can see there, our thumb is then going to be the vector that is perpendicular to these other two, and that will give us which way things are going to go. So in that case, the positive axis indicated by our thumb is coming towards us, which is not what we want. So what that suggests is that we would have to do things the other way around. So we would point this finger in the direction of the principal axis of the camera, and then this finger here, trying not to make any rude gestures, of course, and then this finger in the direction of the up vector, and if we do that, we see now we get the right axis with our thumb. So the right hand rule can be very useful for understanding exactly what vector output we're going to get from the vector cross product. Okay, so what I want to do first is make some changes just to the code that we wrote in the last video. So in the last video we wrote code that created our color gradient image, and we just did that in the CApp class. Now that's not really how we want things to work ultimately. What we're going to do is create a scene class, and the scene class is going to manage all of the objects in our scene. It's going to handle the cameras and the lights and everything else, and the scene class is therefore logically going to be responsible for actually handling the rendering. So the first thing I want to look at today is actually creating that scene class, and so to do that what we're going to do is create a new class, and then we're going to take the code that generates the color gradient image that we saw last week, and we're going to put that into the scene class and then modify the CApp class to use that. And that then leaves us set up really for how we're going to go forward with everything else. Once we've done that, I'm going to talk about camera, how we actually implement the camera geometry that we've just been talking about. Okay, so let's dive in and let's have a look at creating the scene class now. Okay, so I've gone ahead and I've simply copied the code that we created last week into a new directory that I've called EP2 code, or episode 2 code, obviously. Now, it isn't necessary to do that. You can just carry on working in the same directory that you were working in. I do it this way just to keep myself organized between different episodes of the videos. If you're not making videos about them, which I assume you're not, then you don't really need to worry about doing that. So the first thing we're going to do is we're going to create the scene class, and we're going to put that into the QB ray trace directory that we also created last time. At the moment, that only contains our QB image class. So we're going to put the scene class in here. And so let's begin with the scene.hpp file. Okay, so I've gone ahead and created a new file called scene.hpp. And the first thing that we need to do, as we did in all the videos, is define our include guard. So hash if not define scene h, then hash define scene h, hash endif. As we talked about in the last video, these are of course compiler directives. They simply allow the compiler to know if it's seen this header file before, which can improve efficiency. So we're going to do hash include. We need vector from the standard library. And we're going to also bring in, of course, SDL2. So SDL2 slash SDL.h, SDL.h, there we go. And I also need to bring in the image class that we created last week. So we do hash include qbimage.hpp. Okay, and we're putting everything together now in a namespace. Okay, it's not strictly necessary, but it does help with keeping all of the code tidy. So I've created a namespace called qbrt, and I'm going to put all of the classes and everything into that namespace. Okay, so now we're going to define our class, scene zone, remembering the semicolon after the curly brace for a class definition. And let's consider first the public function. So we have initially the default constructor, of course, okay, accepts no input parameters. We're not going to worry about a destructor or anything else. The only other function that we're going to define right now is the function to perform the actual rendering, okay, which is going to return a boolean. It's called render, and it accepts as input a QB reference to a QB image instance that it's going to use for the output, and that's it. That's everything that we need for the scene class. Really there. Let's just for the sake of completeness, we're going to create a space for private functions that will come. Then there are none at the moment, so that will be private there. And we also have, of course, private members, but we're not going to actually define any at the moment. Okay, so save that. That's everything that we need at the moment for scene.hpp. So let's have a look at how we would put together scene.cpp. Okay, so this is, I'm just going to put in a comment just so we know what this is, the file scene.cpp. Okay, and the first thing we're going to do, of course, is hash include scene.hpp that we've just defined, and then I'm going to make the effort to define the default constructor. I mean, it isn't necessarily strictly necessary to do that, but it does help. And notice that as we're using a namespace, we have to put the qbrt namespace and then colon, and we leave the constructor blank for the moment. We then have our function to perform the rendering. Okay, so this is bool qbrt colon colon scene colon colon render qb image reference output image, just like that. Now, this is simply going to actually perform the rendering, which for the moment is really very simple. We're only creating our color gradient image, but ultimately when we go on to really implement ray tracing, the core functionality is going to start here. So first thing we do is we get the dimensions of the output image. Okay, so int x size is equal to output image dot get x size. Okay, and we're going to need to make some changes to our image class, I think, to support that. We'll come to that in a moment. Dot get y size, like so. And then we just have the code that we created before. Hang on, yep, create some color creation. So this is the same code that we wrote before, but I'll just go through it now. X equals 0, semicolon x less than x size, semicolon plus x. And for int y equals 0, y less than y size plus y, like so. And then very simply we do output. No, we don't. No, let's define red and green. Red equals, and then we're going to static cast to double x divided by static cast to double of x size. So that will give us a value that varies between 0 and 1 multiplied by 255.0, and we do exactly the same for green. Static cast to double y, okay, and you can probably see where this is going to go. Static cast double y size multiplied by 255.0. Okay, and now we modify our output image dot set pixel x, y, and red, green, and 0.0. And that's it. For the moment, we'll just do return true for completeness, and for the moment that's everything that we need for the scene class. What we've done there is take the code that we wrote last week for creating the color gradient image, and we've put that into our scene class, okay? And we do need to make some minor changes to the QBImage class that we looked at last week, so let's have a look at that now. Okay, so I'm in the QBImage.hpp file. The only thing that we need to modify here is that we are going to add functions to return the dimensions of the image, and we've already seen why we need those. So we have int get x size and int get y size, just like that. So save that, and now let's have a look at QBImage.cpp. Right, okay, so this is the code for QBImage.cpp that we wrote last week. All we're going to do is put in the functions to return the dimensions of the image, which are going to come here. It doesn't matter where we put them really. I've chosen to put them after the function to set pixels, the function to return the dimensions of the image. Okay, so this is int QBImage : get x size, and that simply is going to return m_x size, and I'm guessing you can probably guess what we're going to do here. Get y size, and that's simply going to return my size, like that. Okay, so that's everything that we need in QBImage. The final thing that we need to do is to make some changes to CApp, the CApp class, so that we can use the new scene class properly. So let's have a look at that. Right, okay, so I'm in capp.h, which is of course in the main directory for our code, not in the QBRaytrace folder. And the first thing that we need to change is obviously we need to hash include our scene class. So that's in ./QBRaytrace/scene.hpp, like so. Okay, and the only thing that we need to change here is that we are going to add an instance of the scene class, and we put that here. Create an instance of the scene class. Okay, like so. It's QBRT because we put it in a namespace, : scene, and it's called scene. Okay, that's the only changes we need to make to capp.h. So let's look at capp.cpp. Okay, so here we are in capp.cpp. You'll notice, if you remember what we did last week, is we initialized our image like that, and then we have the code here to create the color variations. You'll recognize this is identical to the code really that we've just put into the scene class. So obviously what we're going to do, just go ahead and delete that code there. That's it. We don't actually need to do anything else there in our initialize function, so let's just tidy that up and save. And we need to do one last thing when it comes down to, yes, so let's have a look at that. So down in our onRender method, we need to do things here a little bit differently. We don't just display our image now. What we need to do instead is render scene. Okay, so we simply do scene.render image. Now we've already initialized the image as we talked about last week, so we simply pass that to the render function of our scene class, and then we do image.display and everything else, and that's it. That's everything that we need to change. Okay, so let's save that, Okay, so now back at my terminal window, if we look in the QB directory, we now have scene.cpp and scene.hpp that we've just defined. And if I go back to the root directory of that, we made changes to capp.cpp and capp.h. So if I run make now to perform the compilation, or to compile the code, remember, if you're not sure what make does, we talked about that in the previous video, so I'm using gmake to manage my build. If you're using an IDE, of course, it will take care of that sort of thing for you. Okay, so that's done that. So now if we run /qbray, that's the name of our executable, and we just bring that over. Now we see we get exactly the same result that we had before. Now that doesn't seem tremendously exciting, I know, because it's exactly the result we had before. Well, I mean, so what? But what is good now is that we have finally rearranged our code into the structure that we're going to use when we actually really come to implement ray tracing, which is a really an important first step. Okay, what I want to talk about now is camera geometry. And as I mentioned before, we are going to be using the vector class from the linear algebra library that I've developed before. So we're going to just get that from the GitHub repository. There's a link in the description below. And if you're interested in more about that, as I said before, you can simply go and have a look at the videos from that series. Links in the description below, of course. Okay, so let's jump in. Let's first of all have a look at getting the code we need from the linear algebra library, and then we'll go on to look at actually doing implementing the camera class and a class to handle the rays that we want to cast into our scene. Okay, let's look at that now. Okay, so back in our terminal window, I'm simply in the root folder of our project, currently called episode 2 code, of course, and what we're going to do now is have a look at cloning the code for the linear algebra library that I've been talking about. And to do that, I'm going to do it, as I say, from the command line. So I'm going to go into QB ray trace. If you're using an IDE or something like that, of course you can still do this. I mean, there's several ways. You can go to the GitHub website and you can do it directly from there, or you can actually simply just copy the qbvector.h file that we're going to use from the repository. It's up to you exactly how you want to do it, but I use Linux, so I do tend to like doing everything from the command line, so I'm sticking with that. Okay, so I'm in the QB ray trace folder, and what we're going to do is simply git clone, and then we need the path, which is https://github.com, like so, / if I could spell, QuantitativeBytes /qb linalg.git. Okay, and run that. That will then bring down everything from the GitHub repository, and if we now look at our folder, we see that we have now the QB, here we have the QB linalg directory. Okay, so let's have a look at that. So if we go into QB linalg and look at the files there, we see we now have everything from the linear algebra and C++ series that I did before. The one piece of code here that we're really interested in is of course qbvector.h, but do be aware of the README and of course the license terms and conditions that go along with that if you end up using it. Okay. Okay, so going back into the QB ray trace directory, what we're going to do now is create classes to actually implement our rays and implement the camera. So the first thing we're going to start with is a class for handling the rays that we're going to cast around our scene. So we're going to open a new file and we're going to call that ray.hpp. Okay, so I'm in my new file, which I've called ray.hpp, which is in the QB ray trace folder. So as always, we do include guards #ifndef ray h, like so, #define ray h, and #endif. Okay, save that, there we go. And we only need one include file here. We need to bring in our vector class, so we bring that in from /qblinalg/qbvector.h. And it's important to note the QB linear algebra library I did as header only, so we don't need to worry about compiling any code. We just #include the header file there for QB vector, and that really is all that we need. We're then doing everything inside our QBRT namespace, so we specify that, and we're going to create a class called ray. Right. And in here, we're going to have a number of public methods. We have a constructor. We're not worrying about a default constructor. We don't need one for the Ray class. Okay, so we have Ray as a constructor accepts as an input a const reference to a QB vector double reference 0.1 and const QB vector type double reference 0.2. So that will define an array between the two vectors 0.1 and 0.2. Notice this particular syntax that we're using here. So the QB vector class was created using templates. So when we create an instance of the QB vector class, we specify what data type we want it to have. Do be aware, as I said in that video, it's not really designed to work with integers. So it really only allows you to specify single or doubles, but yeah, it was functional for what I wanted it, and indeed it's fine for this. We're going to do everything as part of this library as part of this ray tracing project using double precision arithmetic anyway. We then want functions to allow us to return those 2 points, so we have QB vector double get 0.1, okay, it's pretty obvious, const because it doesn't modify anything, and QB vector double get 0.2, also const like that. And then we have public member functions. Now the members, the data we're going to store in our class, I'm not storing these as private like I normally do because it just makes things a lot more convenient. This is kind of an internal class that's going to be used internally in the ray tracer, so I figured it's not really so important to keep everything private, and it just makes it simpler to access the data that we need. So we need QB vector double m.1. What that will do is you call that specific constructor of m.1 that accepts one integer as input, which will create a vector called m.1 of size 3 elements. Okay, so we have QB vector double m.2 like so, and we need one more, which we're going to call m_lab. Now that may not be obvious what that means, but it's simply going to be the vector that goes from point 1 to point 2, which I've called AB. So from point A to point B, you can see where we're going with that. One thing I always like to do is just tab things out nicely so that they line up. Not strictly necessary, but I think it just improves the look of the code. Okay, and that's everything we need for ray.cpp, so let's save that. And now let's have a look at ray.h, sorry, ray.h, right. And let's have a look at what we need for ray.cpp. Okay, so I'm in my new file, ray.cpp. The only include we need here is ray.h, like so. Okay, right, there we are. And then we're going to define our constructor, like so. Accepts as input const QB vector double reference 0.1. What we could do, we could use templates here, and we could make it so that we could modify our ray tracing code to use single precision or double precision floating points, but I don't really see that there's much point doing that, and I think it's easier, much easier really, just to say that we're going to use double precision floating point for everything. So in our constructor, all we're going to do is simply store all of this data. Do like so, and mlab is equal to m.2 minus m.1. Now the QB vector class overloads the various operators, so it allows us to do that properly. So we just do 0.2 minus 0.1, and that's going to give us the difference between those two vectors. Okay, that's the constructor, and then we just need functions to return the member variables get 0.1 and get 0.2. Strictly speaking, we don't, because we did declare them as public, but I always feel it's good practice to go ahead and define these anyway. So get 0.1 const like so. Return m_1 like that, and QB vector double QBRT colon ray colon get 0.2 const return m.2. Okay, and go ahead and save that. That's everything we need for ray.cpp and ray.h. Okay, so let's move on to looking at the actual camera class, which is now we're going to actually talk about how we go about implementing the maths and the geometry that we talked about at the beginning of this video. Okay, so I am in my new file. This is camera.hpp. Okay, and as always, we are going to do our include class, hash if ndef camera h, hash define camera h, and hash indif. Okay, just like that. And we need a couple of includes. We need to hash include ./qb linalg/qb-vector.h, because we're going to need to work with vectors. Okay, just like that. And we're also going to need to bring in ray.hpp that we've just defined. And this of course goes into our namespace qbrt, like that. Right, so let's have a look. What do we actually need for our camera? Oops, class camera. Okay. So in terms of public members, now we are going to define a default constructor. Okay, so simply camera, that's easy. And we're then going to need functions to set camera parameters. Okay, so we need void. We need to be able to set the position of our camera. So we have void set position. Okay, const qb vector double reference new position, just like that. Okay, and we're going to be able to, we need to be able to set look at. Okay, const qb vector double reference new look at, like so. We need to be able to set the up vector. Okay, const qb vector double reference up vector. Okay, and we need to be able to, one I didn't talk about in the geometry is the length of the camera. All that is actually, it's not a vector, sorry, that is double new length, like so. And all that actually is the distance that of the projection screen, the virtual screen, from the pinhole in the terms that I used before. Okay, so we have the camera location and we have the point that we're looking at, but then we set the distance between the actual pinhole and the screen. Is in the example that I showed was just 1 unit, but actually we want to be able to vary that if we want to, so we have a parameter for that we call camera length. Okay, right, that's that one. We then need to be able to set a couple of other things also that I didn't talk about. One is horizontal size, double new size, and what that is simply the horizontal size of our screen, and the other one that will go with that is of course the aspect ratio. And the reason we do that is so that we can define the virtual screen to be the same dimensions, or the same basic shape as the screen or as the image that we want to create. Okay, so a 16:9 ratio would be equivalent to, you know, 1920 by 1080 for full HD. So we would specify a horizontal size of however many world units we want, so it could be, it's likely to be a fraction of 1, and we then specify aspect ratio as 16:9, which I think is about 1.78. Okay, so we need a function there for set aspect, which accepts a double new aspect. Okay, and that's it for functions to set the camera parameters. We then want functions to return camera parameters. I always think it's important to define functions to return these, and again, like we did with the Ray class, it would be possible to simply declare these as public, but generally, especially for a class like camera that's going to get used more, I really do prefer to use functions to handle all of the parameters. Just my personal preference. So we can call that get position. It could be const, but we won't worry about that. Vector double get look at. Okay, I mean these are all pretty simple. QB vector double get up, like so. Now QB vector double. Now this is one that we haven't talked about. Get u. That's going to return the u vector after we've calculated it and we also have qb double get v. Okay, so they return the u and the v vectors that we're actually going to calculate for the screen, exactly as we saw in the illustrations at the beginning. Okay, and qb vector double get screen center. Okay, center like so, right? And then we have double get length. Double get length, double get horizontal size, or size I've called it, and double get aspect. Okay, those are all pretty self-evident. And finally we need a function to generate array. And this is an interesting one. What this is actually going to do, let me just put some space in there so we can see more easily. What this is actually going to do is return an instance of the ray class, generate ray, and it accepts as input float projection screen x and float projection screen y. Okay, now probably in this video we're not going to really do anything with that, but projection screen x and projection screen y, notice that these are defined as floating points. So what these define is the position on the screen that we want to generate a ray for. So the ray function, generate ray function, is going to return an instance of the ray class that represents a ray that goes from the pinhole out through a particular position in the screen specified by pro screen x and pro screen y. These are floating points, okay, so they are intended to vary between -1 and 1, with 0 representing the center of the screen and -1 or 1 representing the left or right or top and bottom extremes of the screen accordingly. And then, of course, those are fractions of the u and the v vector. So pro screen x represents a fraction of the u vector, and pro screen y a fraction of the v vector. And therefore they translate into positions in the three-dimensional coordinate system when we multiply them by those vectors. Okay, I think if you think about that's really going to make sense. Okay, so we're not going to use generate ray today, but when we come to actually look at implementing something more closer to actual ray tracing, I think it will become obvious why we're doing it that way. Okay, and that's that function. And then we have one last function to update the camera geometry, because there's a few calculations that we have to do. I should just do a full stop. A few calculations that we have to do if we modify the position or the lookout or anything. So it makes sense to have a function to update things. Update camera if I could spell geometry. Okay, right. And we have a number of private members. Of course, we have qb vector type double m underscore camera position 3, like that. qb vector double m underscore camera look at, and these of course are all three-dimensional vectors, so we're specifying them as having 3 elements, right? Okay, so we have qb vector double m camera up 3, qb vector, no, let's do double m underscore camera length, okay, double m underscore camera horizontal size, and double m underscore camera aspect ratio. Okay, and then we're going to need the various private members for things that we're going to calculate. Okay, so we have qb vector type double m underscore. Now I've called this alignment vector. This is actually the principal axes of the camera that we've been talking about. I'm going to tab that out to there. We then also have qb vector double m projection screen u. Okay, it's 3 elements. They're all 3-dimensional vectors. Double m projection screen v. Okay, and qb vector double m underscore projection screen center. and just tab those out. Really not necessary to tab things out like that, but I just think it just looks a bit cooler in my humble opinion. Okay, so that is everything that we need. Let's just put in a blank lines there, we don't need those, and let's save that. So that is camera.hpp, okay, all of the things that we need. Right, so let's have a look at what we need for camera.cpp. Okay, so here we are. This is camera.cpp, okay, and we're going to need to bring in a number of things. We need to hash include, of course, camera.hpp that we've just defined. We also need to hash include ray.h, and we need from the standard library hash include math.h as well. Okay, like so. Let's save that. There we go. Now, okay, constructor first. qbrt : camera : camera. Okay, this is our constructor, a default constructor for the camera. So let's say this is just the default constructor, and I'm arranging things so that we only have a default constructor rather than one that accepts all of these as inputs. So what I'm going to do initially is just define these as being what we need. So that's std. So these are going to be the default positions. Okay, so the QB vector class you can specify it with a non-default constructor if you wish, and we can then pass to it the data we want using an std vector instance. Okay, like so. And we've got 0.0 minus 10.0, 0.0. These are just default parameters, really. In reality, you're probably going to want to vary these, but it just means that if we construct a camera using the default constructor, then we get something that's, makes some kind of sense. Not strictly necessary, but I just think 0.0, 0.0. So we have a camera that is 10 units away from the origin on the y-axis, looking at the origin, and we specify camera up is qb vector double, std vector double, and obviously 0, 0, and 1. Okay, that specifies the up direction, and we're going to set m camera length, the default, to 1, and m camera size, horizontal size, default was 1, and m camera aspect, ratio, also equal to 1. And that's it for our default constructor. Now, unsurprisingly, we're going to need functions to allow us to set these. So void qbrt : camera : set position. Sets const qb vector double reference new position, just like so. And really simple. This is simply going to do m camera position equals new position. That's it. And then we have void qbrt : camera : set look at const qb vector double reference new look at m underscore camera look at equals new look at. Really obvious. qbrt : camera : set up to set the up vector const qb vector double reference new up. Oh, I didn't call it that, let's call it up vector. Pretty doesn't matter really. Camera up equals up, up vector, just like so. I'm going to put in some blank lines there. Okay, we have void qbrt : camera : set length double new length m underscore camera length equals new length. I think these are all probably fairly self-explanatory, really. Set horizontal size double new size m underscore camera size equals new size. Really obvious. Okay. But has to be done. Void, come on, void qbrt : camera : set aspect double new aspect m underscore camera aspect ratio equals new aspect. Okay, Alright, and then we have our functions to return the various parameters. This is all a little bit boring, isn't it? But I think it's important to have all of these methods to return the position of the camera. Okay, Q returns the type of QB vector double, like so, QBRT : camera : get position. Let's simply return m camera position, just like that, and then method to return the lookat of the camera, QB vector double QBRT : camera : get lookat, return m underscore camera lookat. Okay, really obvious. Method to return the up vector of the camera, QB vector double QBRT : camera : get up, just like that, and simply return m underscore camera up. Okay, really basic. Method to return the length of the camera, which returns a double QBRT : camera : get length, return m underscore camera length, just like that. Okay, nearly there, promise. Method to return the horizontal size of the screen, which is a double QBRT : camera : get horizontal size, return m underscore camera pause size, like so. And we have method to return the camera aspect ratio, double QBRT : camera : get aspect, return m underscore camera aspect ratio. Really obvious. Okay, and then we have the functions that return the calculated parameters. So method to return the u vector, okay, which is not a double, it's a QB vector of type double, QBRT : camera : get u, return m underscore projection screen u. One thing we could do there is we could put in code to verify that they have actually been computed before returning them. I'm not bothering with that. The way the QB vector class works, I think it will return a vector of zeros, sensible values, if you call this function without actually calculating the vectors first. But yeah, I mean, probably to be proper about it, we would want to create functions to do that. We also have method to return the projection screen center. Okay, QB vector double QBRT : camera : get screen center, return m underscore projection screen. I bet I've made a few typos in all of this. We'll see when we come to compile it. Alright, finally. Now, we get to something a little bit more interesting, right? So, what we need now is the function that's actually going to calculate the geometry, that's really going to do all of the work that we were talking about right back at the introduction of this video. So let's look at that. This is the function to compute camera geometry. If I can spell. Okay, right. So, return type void QBRT : camera : update camera geometry. Okay, so first of all, we're going to compute the vector from the camera position to the lookat position. This would be the principal axes of the camera that we talked about in the introduction, which here we've called alignment vector. So if m underscore alignment vector is equal to m underscore camera look at minus m underscore camera position, right? So that gives the vector that is simply the difference between the position and the look at. So, and then we want to normalize that because we're only interested in the direction. We don't need to worry about the length of it. So we do m alignment vector dot normalize, like so. Okay. So secondly, we're going to compute the u and v vectors. Okay. So we have m underscore projection screen u is equal to qb vector double colon colon cross. So the cross product function in the vector class is defined as static, so we can call it without reference to a specific instance of a class. So we want the cross product between the alignment vector and the up vector. Okay. Now we talked about that in the introduction. About how that relates to the view, to the u vector, simply that. And then just to be sure about things, you do m projection screen u dot normalize, okay? And we're going to calculate the v vector. This is the same, m projection screen v is qb vector, type double colon colon cross with the cross product, m projection screen u that we've just calculated, and m underscore alignment vector, just like that. And we're going to normalize that as well. M projection screen v dot normalize. Okay. So that will give us the u and the v vectors. And then thirdly, compute the position of the center point of the screen. Okay, this is an easy one. So the position of the center point of the screen is, well, it's called m projection screen center, and it's simply the camera position plus camera length, m underscore camera length, sorry, m underscore camera length multiplied by m underscore alignment vector. Okay, and that's pretty straightforward. So starting from the position of the camera, that's where the pinhole is, we just move along towards in the direction of the alignment vector, or the principal axis of the camera, so towards our look at, however many units are specified by camera length. Okay, and finally we're going to modify the u and v vectors to match the size and aspect ratio. So at the moment u and v are unit vectors, so they're exactly 1 unit long. We're going to modify their length to better represent the dimensions of the screen. Projection screen u equals m underscore projection screen u multiplied by m underscore camera horizontal size. Okay, and m projection screen v equals m projection screen v multiplied by m underscore camera horizontal size divided by m underscore camera aspect ratio. So that will modify the u and v vectors to match the dimensions and aspect ratio of the screen. Okay, and that's it. That's the implementation of the geometry that we talked about in the introduction. I did say that, actually it's not perhaps as complicated as it does seem. We're just using two vector cross products to calculate u and v from the information that we have already defined about the camera. As I said before, if you want to know more about the vector cross product, I suggest go back and have a look at the video from the linear algebra library where I talked about implementing that code, and there's, I think, hopefully a reasonably good explanation of that over there. There's a link in the description below, of course. Okay, so let's carry on. So the last thing that we need is our function that's going to return a ray cast from the center of the camera out through the screen at a particular point. So this is qbrt colon colon ray. It returns an instance of the ray class, which is part of the qbrt namespace, hence we have to do that. And then we have qbrt colon colon camera colon colon generate ray, and this accepts as input projection screen x and float projection screen y. Now we assume that those are values between -1 and 1. So the first thing we're going to do is to compute the location of the screen point in world coordinates. Okay, that's what we want to do. So we want to take from our UV coordinate system and map that to our XYZ world coordinates. Projection screen X and projection screen Y, by the way, these are in the UV coordinate system. Okay, hopefully not too confusing. All right, so we have QB vector type double. Okay, screen world part 1 is equal to m underscore projection screen center, that's the center location of the screen, plus m underscore projection screen u multiplied by pro screen x, right? I'm taking my time over that, just want to make sure I've got it right. So whatever our u vector, we multiply projection by projection screen x, so that's between -1 and 1, so that gives us some fraction of our u vector, and then we simply add that to the position of the center, and that's going to give us the u ordinate transformed into world coordinates, but that's not quite the final result that we want. We need to define another vector. This is going to be screen world coordinate. The final one is going to be screen world part 1 that we've just defined. Okay, plus, and now that same calculation, projection screen v multiplied by pro screen y. Just like that, and that will give us the final thing. And so what we're going to do, use this point to, yes, use this point along with the camera position to compute the ray. Okay, so screen world coordinate that we just calculated, that is the equivalent point mapped from it. So we start from a pixel location in x and y, and we normalize that, and then between -1 and 1 in both axes, and that's in our UV coordinate system, and then we're transforming that into our XYZ coordinate system, and which is called screen world coordinate as the final result, and then we simply return QBRT : ray, return an instance of the ray constructed between camera M camera position and screen world coordinate. Okay, and that's it. Let's save that. That is everything that we need for our camera class. Now, as I said, I wouldn't be at all surprised if I've made a whole bunch of typos doing all of that. So what we're going to do now is I'm going to go to my terminal window, and we're just going to check that everything compiles, and then we're going to have a look at how we can actually create some test code to really show that this is working. Okay, so at my terminal, so we can see we've created ray.cpp and ray.hpp, as well as camera.cpp and camera.hpp. If I go back to the root folder, because we made the effort in the first episode to create our make file, in order to compile everything, we can just run make, and that should pick up the new files automatically. And immediately we see we've got a problem. ray.cpp. Okay, line 1, hash include ray.h. I did of course call it ray.hpp, so let's have a look at changing that now. Okay, so in ray.cpp, of course we bring in the file there, hash include, it should be ray.hpp. My mistake. Okay, now hopefully there aren't too many others. So back at our terminal, let's run make again. Ooh, okay, alright, well that's okay, so we've compiled. Okay, right, that is my mistake. I used round brackets here. These clearly should be curly brackets. So that is in ray.hpp. All right, let's have a look at that. So ray.cpp, apologies. Okay, so in ray.hpp, yeah, these need to be curly braces. My mistake, I should have known that. Okay. And that's going to crop up elsewhere as well, where we've defined those, I think. So, well, let's try compiling. Let's save that. Back to our terminal window, run make. Okay, so ray is finished with, and now we see we have problems. Again, I made the same mistake there, fatal error in camera.cpp. Let's have a look at that. Okay, so in camera.cpp, of course, we changed that to ray.hpp. That was a bit careless of me. make. Okay, we're getting a whole bunch of errors, which I was expecting because, yes, we need to define those using curly braces as we just saw. So let's have a look at that. So camera.cpp, here we go. These all need to be curly braces, not round braces. And same for these. Sorry about that. Save, and we're going to try compiling again. Okay, ration, camera ration, line 45, so line 45, yep, camera ratio, right, careless, save that, and get back to here, try again. Normalize, did you mean normalize? With a Z, I did. So in camera.cpp, which is this file, where we did the calculations, here we go, this is normalize, where are we? Normalize there with a Z, okay, that's important. Okay, I think that's it, save that, and back to the terminal. Okay, so everything compiles. If we run that, we just get exactly the same result that we had before. Of course, because we haven't done anything that would have actually modified the output. Okay, so let's close that. So what we need to talk about now is how exactly we're going to test this. We need to be sure that our code is generating the correct camera geometry. And what we're going to do is have a look at the U and V vectors and the projection screen location. And we're going to define a simple camera and check that those are what they should be. So in order to do that, this isn't going to create any kind of graphical output, so it's a bit dull, but you know, it's functional. More interesting things will come in later episodes, I promise. What we're simply going to do is write those out to the terminal. So in order to test that, we're going to go to our capp class. So first of all, capp.h, and then we're going to look at capp.cpp as well. Okay, so let's do that now. Okay, so in capp.h, first thing obviously we're going to do is we need to bring in /qbraytrace/camera.hpp. That makes sense, doesn't it? And simply save that, and we don't need to do anything else. Okay, and now let's have a look at capp.cpp. Okay, so here we are in capp.cpp, and let's see, what do we need to do? Okay, what I want to do here is I want to bring in, first of all, our vector class /qbraytrace/qblinalg, okay, /qbvector.h, just like that. Save that. Now, let's have a look. Okay, my apologies, there's one more thing that we need to do. In capp.h, let's just go back to that. So what we need one private function. It's really only for debug, but we're going to define it here anyway. It's called print vector const qb vector double reference input vector. And the point of this is simply to allow us to display a vector. I've done that wrong. Print vector. There we go, like so. Okay, right. So it's simply a very basic function that's going to allow us to print a vector out to the terminal so that we can see what the actual values are. Okay, so first of all, let's go back to capp.cpp. All right, capp.cpp, right down here at the end, we're going to define a new section here for private functions, right? And we have void capp : print vector const qb vector double reference input vector. Okay, this is pretty basic code, and it's the same as the code I used during the linear algebra series. So I have talked about it before in that video, but we will cover it here. So we have a number of rows is input vector dot get numdims. Okay, and then we're simply going to loop through each one for int row equals 0, row less than n rows, semicolon plus row, basic, right? And we do std cout, std fixed because we want fixed precision, std : set precision. precision. This is a handy technique actually to, if you want to display things to the terminal very neatly, we can do that, and we'll set precision to 3, and then we're going to plot input vector dot get element, gets a single element, row, and std : nl semicolon. Right, and that's it, and save that. That is our private function print vector. Okay, I think the operation of that is pretty basic. So let's go back up to the top. So here we are. So we're still obviously in capp.cpp. What we're going to do is, right in our initialization code here, we are going to do our testing. Okay, so we are going to test the camera class. Right, so we're going to create an instance first, qbrt : camera, test camera. Now I'm not going to accept the default parameters from the constructor. We're going to set everything up as we want. In fact, we're going to set everything up to match the geometry that we used when we created in the animation at the beginning. So set position, QB vector double initialized with std vector double 0.0, 0.0, 0.0. So we define our camera at the origin, and we're going to set look at to be some position along the y-axis. Okay, double std vector double. Okay, and we want 0.0, 2.0, 0.0. So the look at is 2 units away in the y direction, the positive y direction. We're going to set the up vector curly braces there, 0.0, 0.0, 1.0. Do be careful about the curly braces and round braces. Okay, test camera set length 1.0, test camera set horizontal size initially to 1.0. These are the default ones, but we'll just make sure everything works as it should. Set aspect initially to 1, so that will give us a square screen. And then we're going to call test camera dot update camera geometry. Why do I always get that wrong? Camera geometry like that. Okay. Now, in order to make sure that that actually does work, we of course want to display the results. So what we're going to do is we're going to get the screen center and view the vectors and display. Okay. So we can simply do auto screen center. I'm using the auto keyword there so the compiler will easily derive what data type this should be, so we don't need to specify that ourselves. And we have get screen center. Okay, auto screen view equals test camera dot get view. Okay, and auto screen v equals test camera dot get v, just like that, and display to the terminal. Alright, so let's first of all std : cout camera screen center std nl, right, like that, and then we just do a print vector because we define that screen center. Okay, and then std : cout, going to do /n for a new line, camera u vector colon std nl, and print vector screen u. Okay, and you can probably guess what's coming next. /n camera v vector std colon nl, print vector screen v semicolon. Save. Right, that is everything that we need now, hopefully, to test the camera class. So we're going to try compiling it, and then when we run our code, we should hopefully see the results that we want. So let's go to our terminal. There it is. Now if I run make, that will hopefully compile. Nope. Right, yeah, of course. So capp.cpp line 120. Okay, capp.cpp line 120. Yeah, there we go. That, of course, should be a round bracket. Okay, right, so save that, back to our terminal, run make. Okay, that's good. So let's run /qbray, and that will produce the same image that we've seen before. It comes up on my other window. We've seen that 100 times. We don't really need to see that. What we're particularly interested in, though, is the information we have here. So we defined a camera at the origin, pointing or looking at a point 2 units away in the positive y-axis, and we defined the camera length of 1. So the screen center should be 1 unit away from the camera in the positive y direction, and indeed that's what we see here. So camera screen center 0, 1, 0. The camera u vector should point in the positive x direction. Okay, if we think about the geometry, right? So we've got the alignment along, this is the y-axis, and then we've got our up vector. So if that's y and that's z, this axis must be x. Okay, the right-hand rule was explained before. Okay, apologies if that looks like a rude gesture, it's not meant to be. Okay, so the u vector, we have positive 1 in the x-axis, and then 0, 0, minus 0 is close enough, is 0 basically. And the camera v vector then should be perpendicular to that, and we see that it points vertically upwards, 0, 0, 1. That is exactly what we would expect. Okay, and you can play around with the position of the lookat and the position of the camera and verify that those results do indeed change to give what you want. Anyway, that's everything that I wanted to talk about today. This has become rather a long video, more so than I expected actually. We've covered a lot of ground. We've covered all of the geometry for how the camera works in terms of ray tracing. We've looked at how we can clone the code that we need from my linear algebra library to do vector arithmetic, and we've looked at that. And then we've also gone on to look at modifying our code to created the scene class, which is going to take care of all of the rendering, and we moved our test render code out of the C class into the scene class. And then we went on to create classes for handling rays that we're going to cast out into the scene and around the scene for reflections and light. And then we created a class to handle the camera that then takes care of computing all of the geometry that we talked about in the introduction at the beginning. And we've done the very basic testing there just to see that it works. So we don't get any really interesting output from our code yet. Apologies for that, but that will come. Baby steps and all. We really have to work through this, one step at a time, but more interesting things will come, I promise. So in the next video, we are actually going to start talking about ray tracing itself, and we're going to talk about ray-sphere intersections, and we are going to produce an image of a sphere, but that's coming in the next video. Anyway, listen, I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked it, please do remember to hit that like button, and if you haven't yet subscribed to my channel, please consider doing so and hitting the bell icon for notifications so that you don't have to miss any future videos. Like I said, the next video we are going to start doing ray tracing, and we will produce an image of a sphere, so if you haven't subscribed already, please do so you don't have to miss that. Anyway, listen, it's been a pleasure. I really hope you've enjoyed it. Thank you very much for watching, and I really look forward to seeing you in the next video. Bye!